La 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 la.
What you doing, buddy?
I'm doing math hands.
Math hands? What do you know about math hands? Do you even have hands?
This.
Do you even have hands? You call these hands?
You can't.
These are like little baby hands, buddy. What is that?
I can
Do you even know what that is? I don't think you know what that is. What is it equal to?
It's a natural log of 2.
Oh, it's not. Really? Do you
Yeah.
even know what that means?
Duh.
Duh. Oh, really? How do you write that?
Okay.
Really? You're going to write it with the eraser?
L.
Dang, you got chops, dude. How did you figure that out?
I use my fingers.
You used your fingers? Good job, dude. Ladies and gentlemen, welcome. Another chapter here in calculus. Today we're talking about bridges. Beautiful bridges. Some bridges were made to adorn and be functional and be painted. Beautiful stuff. Other bridges were made up to light up the sky. Some bridges float on water. Some bridges float on air. It's really, the idea of bridges is a very, very natural idea. Some bridges even make you laugh and win Academy Awards. But the bridges that we're talking about today are more like these bridges. Bridges between functions. Functions that are incredibly hard often to evaluate or take derivatives of or add or integrate or whatnot. Some of these are very, very difficult to deal with. Consider this a whole different world as compared to this world. The world of polynomials is a totally different idea here. It's incredibly easy to evaluate. If you can multiply and add, you can evaluate these. Taking derivatives is easy. Taking integrals is easy. You can almost say that everything is easy here. And everything may not be so easy here. We talked about this before. This is like the world of Mondays. Today's Monday. Mondays and Tuesdays. Today's Monday. Tomorrow's Tuesday. The next day's Monday. The next day's Tuesday. It's a hard world. This world over here is a world of Fridays and Saturdays. Today's Friday. Tomorrow's Friday. The next day's Saturday. Next day's Friday. Whatever you want. It's an easy, easy world. And you can get with this or you can get with that. That's why it's exciting to think that what if there was some bridge that linked these two ideas? Wouldn't that be amazing? If there was a bridge that said, you know what, every one of these, I can really use this bridge to cross over here, and maybe it's equal to one of these polynomials. It's more than a bridge, it's a dictionary where questions and integrals and derivatives here become questions and integrals and derivatives here. So whatever you can do over here, you can do here with the polynomials. That would be an amazing bridge right there. That would be worth price in gold if we could find that bridge. Well, guess what? Today, we're not going to find such bridge. It's not your lucky day. So forget about it. That would be a pie in the sky. However, what we can do today is, we talked about this before, about geometric series. If you recall the lesson from geometric series, we said that geometric series are the fairies of series because they're so easy to compute. Well, today we're going to ride the ferry instead of crossing the bridge. This will have to be another day. So forget about it. Instead of doing that, what we're going to do is we're going to ride the ferry. Not that ferry. We're going to ride a different ferry. This kind of ferry, like the boat kind of ferry. And we will, I know what you guys are thinking. No, we're not doing that. We're riding the ferry. I don't know. It takes us across there. It's not exactly the bridge, but it's another way of doing it. Exploiting the properties of the geometric series. That's what we got to do today. Okay? And it starts like this. Wait, let me just finish. We will ride the ferry. I don't know how to spell ferry or which ferry I'm talking about, but let's just guess it's that one. And maybe this, well, we'll have to do it another day. We'll cross that bridge when we get there. Maybe on a different day. So it starts with this basic idea that you learn in junior high. If you have x squared minus 1, you can factor that polynomial into these terms, right? And then the idea is to try to see if you can generalize that. If you were to take that and change it for a 3, what would happen then? I bet what would happen is you'd get something like this. X to the third minus 1 is equal to x minus 1 times all that. And then you could go on and you could factor that. It would become x to the fourth here, x minus 1, and then the sum of all the x's here, x to the third, x to the second. You see they decrease in power. starting with 1 less than 4, because you've got to factor 1 of the x minus 1's here. X to the 5, obviously you continue the pattern here. And then you do something clever here. We divide both sides by this piece. If you divide both sides by that piece, it gives you this. And that right on the right hand side looks exactly like a geometric series. That's why these are the fairies of series. They're the easiest ones in the world to add. It's customary to write it this way. Notice what happens with the 4 there and the 5, the pattern. If you were to switch it to 6, that would be, take it one more to 5. Of course, if it was 7, that would, you'd have to add up all the powers of x all the way up to 6, one short of that, and so on and so forth. So that gives rise to the very, very famous formula: the sum of all the powers of x, starting from 0 all the way to pth power, is equal to x to the p plus 1 minus 1 all over x minus 1. I'm going rather quickly because we've covered this in previous videos, so it should be just a little refresher. If this is too quick for you, play it in slow motion. Or no, I'm just kidding. You should go back and watch the other videos. That would be the appropriate thing to do. Anyways, some nice things happen here when you make p go to infinity. And under good conditions, if your absolute value of x is less than 1, this piece right here, that piece right there will go to 0, because you're taking something that's smaller than 1 and raising it to infinite many powers. Here, that will go to 0. And you'll see this disappear from the formula, and you just have negative 1 over x minus 1. But really you can multiply top and bottom by negative 1 to write it in the more standard form, more familiar. This is what happens under these conditions. If your absolute value of x is less than 1, you would get exactly that. Capiche? Again, this is a review, so we're going rather swiftly through this just to make sure everybody's on the right page. Am I on the right page? Alright, so this formula looks like that so long as this condition is met. Okay, we're adding infinite many powers of x. Alright, what does that have to do with our bridge? What in the world does that have to do with this? Or this, or that? I know, huh? So, so here's what it has to do. The main idea. You would go on and you can, another way to rewrite this is just actually expand it here. 1 plus, that's when x is equal to 0. When x is equal to 0, that's when n is equal to 0, x to the 0 is 1. When x is equal to 1 is x, x squared, all that. That's the left hand side. It's equal to the right hand side. Watch what happens now. You want to generalize this idea and not be so limited to just x. Really, this is a template that would work for anything. It would work if x was not x, if x was t. It would work if x is blah. It would work for anything, any kind of fill in the blank here. So long as this condition is met, as the absolute value of that blank is less than 1. You'd have this excellent formula. And what that turns out to be is, of course, our very, very, very first bridge. Because look, on the left, right-hand side, you have something that's not a polynomial. It's a rational function. And it's equal to, on the left-hand side, a polynomial. And there it is. Thank you, fairy. We're writing the fairy. Using the fairy concept, we see our very, very first bridge between the two worlds. The world of non-polynomials is equal to a polynomial. Amazing. But wait, there's more. That's nothing. Wait till you see what's coming up next. Suppose we wanted to write the expression for that guy right there. We wanted to look at that and say, hey, that's not a polynomial, but can we write the bridge equivalent using our dictionary here? Is there some sort of equivalent expression to that that's actually a polynomial? And the idea would be yes. All I have to do is fill in the blanks here. I start with the right hand side. That's the key right here. I'm going to start with the right hand side. What I want here is 1 over 1 minus x squared. That tells me that whatever goes in the box should be an x squared. So on the right hand side I should have 1 plus x squared plus x squared squared. The stuff in the square is x squared. So this would be x squared to the 4th, and on and on and on, x squared to the infinity. So this is exactly the bridge. So this tells me that 1 over 1 minus x squared is equal to 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th, and on and on and on. Yippee-ki-yay, there's your second bridge. A function that's not a polynomial is equal to a polynomial. I told you. Second bridge. And if you wanted to get fancy, you could write it this way. X to n as n goes from 0 to infinity. This is just another way of abbreviating this. That's equal to 1 minus x squared. Nice, huh? Alright, that's the main idea. We're going to exploit the properties of the ferry here. We're going to ride the ferry, milk the ferry until we get a lot of these bridges. Some of them anyways. We're not doing the main one today because it's not your lucky day today. But it gives you something to look forward to in our next videos. For now though, let's just focus on milking the ferry here, riding the ferry. Let's do a few more examples. Come back and see a couple more of these. Okay? Peace.